Thank you. It's really great to be here. I'd love to thank the organizers for this really wonderful conference, which I think embraces explicitly the defining feature of this discipline, machine learning, and we'll be getting to that shortly. So this talk is going to be about prescriptions for universal learning. It's going to touch on a number of works that I've done with incredible collaborators, some of whom I've listed here. In this talk, I'm going to be asking a lot of questions. And the first question that I'll ask you, and don't be shy, feel free to just speak up, is what do you think defines machine learning and how is it different from statistics? So you're talking to your friend who doesn't really know that much about data science, AI. They say, what do you work on? You say machine learning, and they say, what's that? How is it different from statistics? What's your answer? More complicated models? Okay, good. There's more than one right answer. Mhm. Prediction versus, so machine learning cares more about prediction. Mm-hmm. Anything else? And that's considered more in which of them? Machine learning, okay. Non-stationarity or something? Mm-hmm.
Most papers assume that the machine learning assume that you know the distribution.
Okay. Mm-hmm. Yeah, so quite often the assumptions are a bit different. Different inductive biases. What's the title of this conference? So if we were looking for one keyword that might define the difference, what would that be? Automation. So I think everything that people said is correct, but perhaps that's all a symptom of a different ambition. I would contend that machine learning is really focused on developing intelligent autonomous systems that can learn and make decisions without human intervention. Statistics is not generally focused on that goal. Instead, it's focused on building tools to help other statisticians to analyze data. In many cases, statistical tools can be useful in machine learning, but because these two disciplines have distinct ambitions, quite often we see different focuses, different types of methods might be favored, etc. And really what defines machine learning as a field, I would say, is automation. And so in some sense, AutoML really is just machine learning, but it's making this ambition explicit, which I really like, because I think perhaps we don't critically reflect enough on what we're ultimately trying to achieve and what we're doing and what approach is actually going to get us there.
If you don't mind questions.
Of course.
For you, there's no difference between machine learning and automated machine learning, just the fact of making it explicit, or do you see any other machine learning?
So I think if you looked at, say, the proceedings of ICML and you looked at the proceedings of this conference, you would see sort of a distribution shift to some extent. Although I would say that the key feature of machine learning as a discipline is trying to build intelligent systems that don't require human intervention. And we're getting ever closer, hopefully, to being able to do that. And I feel that AutoML makes that ambition very explicit and focuses on approaches that will particularly help in that objective. I would say machine learning is very broad as a discipline, and so it's does include sort of all sorts of different elements, some of which look a lot like classical statistics. But in the end, I do feel like AutoML is ML, and it's making what we're trying to do very clear and providing a focused approach towards trying to achieve that end. But of course, there's room for other perspectives on this as well. So how is this actually possible as an ambition in light of results like the no free lunch theorems? So when I started my PhD, I'm no longer a PhD student, but I was a while ago. And when I started my PhD, I was working on Gaussian process kernel learning mostly. How do we automate kernel selection for Gaussian processes? I had started working on a problem in Bayesian econometrics where I was using a GP with a particular covariance function. I was looking at RBF kernels, Mathieurin kernels, standard choices, etc. And I found even the hyperparameters of those kernels had a huge effect on performance. And so this made me wonder, well, how do we even know which kernel is the right kernel to use for a particular problem? And can we automate that process? And that became sort of an obsession. And after I'd started to develop a few approaches like spectral mixture kernels, deep kernel learning, etc., and I presented those approaches, sometimes there'd be a learning theorist in the audience who would raise their hand and say, well, what about the no free lunch theorems? Like, what specifically is this kernel learning approach intended to solve? Like, what application setting are you considering? Because we know from the no free lunch theorem that like no single learner can be good for every problem, every model is equally good in expectation over all problems, et cetera. And so at that time, I would sort of think, okay, well, maybe if we think of this as a generative model for the data, it would generate sort of quasi-periodic structures, et cetera. And so maybe we want to use these kernel learning approaches for problems that have seasonal effects, et cetera. Now I would have a different answer, and that answer is the no free lunch theorems are irrelevant to how we should think about model construction in machine learning. And we'll get into that shortly. And this talk is really going to be about trying to understand a foundation for how we should approach model construction. And we'll initially use that foundation to get some clarity on generalization behavior in deep learning that has been specifically associated with neural nets and often considered to be quite mysterious. We'll argue that it's really neither. We can understand this very intuitively as well as rigorously using generalization frameworks that have existed for many decades. And we can reproduce this behavior using other model classes. We'll then get into what really is a bit different about neural nets, including the relative universality of transformers, the geometric properties of their loss landscapes, their relatively impressive ability for representation learning in high dimensions. Okay, so let's have another question. Let's suppose we have these airline passenger numbers indexed by time, and we'll consider 3 different modeling choices that we could use to fit the data and make predictions up until 1961. A linear function, a cubic polynomial, or a 10,000th order polynomial. You might not like any of these choices, but let's say you had to go with one of them. We'll take a poll. Who's going to go with the linear function? Raise your hand. The cubic polynomial, raise your hand. The 10,000th order polynomial. Okay, very good. Have you heard me ask this before? Okay, who has not heard me ask this before but has raised their hand for 10,000th order polynomial? Okay, okay, very good. So I'm going to argue for that. And if I'm unhappy with it, it's because it doesn't have enough parameters. It's really not expressive enough. And even though barely anyone raise their hands for the third choice, I think implicitly we're often making this choice in practice. So in deep learning, it's not uncommon to use neural nets that have tens of millions of parameters to fit problems with tens of thousands of data points. We see models like the ResNet 164 used on CFAR10, which has 50,000 training points. But even before deep learning became popular again, we were embracing models with an infinite number of parameters in non-parametric statistics. And some of those models were actually derived as infinite limits of neural nets. Like Radford Neal showed that if you take an infinitely wide Bayesian neural network, you get a Gaussian process with a particular type of covariance functions. And GPs with other popular covariance kernels like RBF kernels are in many ways like using an infinite order polynomial. You have an extremely expressive model, but it doesn't overfit because it has certain soft preferences for particular types of solutions over others. And so the reason in principle I would go with choice 3 is because I believe the real world is a very complicated place. It has a lot of nuanced structure, and I want to represent my honest belief that that structure is there. I know that there's some setting of the parameters, the AJs, that will get me closer to the ground truth solution that could possibly be managed by choices 1 or 2, which are just special cases of choice 3. But it doesn't end at just wanting an expressive model. We need to combine that expressiveness with some sort of simplicity bias. Okay, so another question. What makes deep learning different? Any ideas? Classical statistical models. Feature extraction, so sort of representation learning. Think about the question I just asked with airline passengers. Yeah, over-parameterization. Lots of parameters, in fact, often more parameters than we have data points. Anything else? If you're thinking about generalization behaviors, are there any generalization phenomena that might come to mind that you've heard about?
I mean, the assumption that other data would plug in, make better predictions.
So this kind of transfer learning that happens with neural nets, like, or the foundation model paradigm kind of. Yeah, so these are all good answers, in some cases too good. I would say commonly people consider overparameterization to be a special feature of deep learning, benign overfitting, the ability to fit signal perfectly, but, fit noise perfectly, but still generalize well if you're training on structured data, and a phenomenon called double descent, whereas you increase the expressiveness of your model. First, your generalization error decreases as you capture more structure in the data, then it increases as you start to overfit, and then it decreases again to a value lower than it did in this first kind of classical regime. And that second descent usually starts around the time that you have about zero training loss. So I'm going to argue that actually none of these phenomena are distinct to neural nets. They can be reproduced using other model classes. They can be intuitively understood through a notion of soft inductive biases, and they can be rigorously characterized using generalization frameworks that have actually existed for many decades. Benign overfitting, by the way, was made famous in a paper about 10 years ago called Understanding Deep Learning Requires Rethinking Generalization. So they showed that convolutional neural nets could fit CFAR images with random labels perfectly, but still generalize on structured problems. And this was seen as in the face of everything we know about generalization, because conventional learning theory measures like VC dimension and Rademacher complexity essentially measure a model's ability to fit noise, and so become quite vacuous for those types of models. So I've mentioned soft inductive biases as a perspective that we can use to try to understand this behavior. Quite often we think of inductive biases in terms of what are called restriction biases. So inductive biases, first of all, is just a fancy expression for assumptions. And when we're doing machine learning, we're learning by example, and we can't do that without making some sort of assumptions. It might feel like in modern deep learning practice, somehow we're not really making assumptions anymore. We are, otherwise, things wouldn't work at all. Those assumptions just tend to be a little bit less explicit than they used to be. One popular way of representing our assumptions is to constrain the expressiveness of our hypothesis space. So use the low order polynomial instead of the high order polynomial, for example, in the last question that we considered. Another example could be in neural net architecture design. Start with a fully connected layer, remove a bunch of parameters, and enforce parameter sharing to get a convolutional layer. We can alternatively just have a soft preference for certain types of solutions over others in combination with an expressive hypothesis space. So I would say Gaussian processes do a good job of representing that principle. They're very expressive models, often more expressive than any neural net you can fit into memory, but they do have very strong but soft preferences for certain types of solutions over others. So in this figure here, we're starting with a restriction bias where we have a uniform preference for different types of solutions. Separately from how well they fit the data. And then we relax that into a soft inductive bias with stronger preferences for the solutions in darker blue. And there are many ways to represent soft biases. So you can do this implicitly through the size of the architecture, for instance, the optimizer that you're using. You can do it explicitly through regularization, through Bayesian priors, and so on. Okay, so let's return to that polynomial example and consider how we could have an arbitrarily large polynomial that would still have this desired generalization behavior that we've been discussing. So what we're going to do now is we're going to penalize the coefficients of the polynomial in a way that's proportional to the order of the coefficient. So we're going to have a stronger penalty for the norms of the higher order coefficients than the lower order coefficients. And so what that's saying is we have a very expressive model class, but if we can fit the data using the lower order terms, we're going to try to do that as best as possible before moving to the higher order terms. And so if we expose such a model to data that looks like it's basically on a straight line, it will fit it essentially with a straight line like we see in the panel on the left. And this is a 150th order polynomial with that order dependent regularization. In the brown curve, we see what happens if we don't have regularization. So that looks like overfitting. If we then increase the number of data points available to us and the structure of the problem gets naturally more complex, the model will adapt its complexity as needed, but it won't prefer an overly complex solution. Okay, so this leads us to another question. Should we use a different model depending on the amount of training data points available to us? And to make this more specific, let's imagine that we're considering models with different numbers of parameters. So if we go back to that airline passenger example, if there were 100 data points or 100 million data points, should we use a different model to train on that data? So raise your hand if you think, yes, we should use a different model. Raise your hand if you think, no, in theory, we shouldn't use a different model. Come on, this is the AutoML conference. Of course, we shouldn't use a different model. We want the same thing that works for every problem, right? And why shouldn't we use a different model? Because typically we don't believe that the complexity of the process that generated our data depends on how many training points we happen to have access to. And a good principle for model construction is to honestly represent our beliefs in our model. And we can see what happens when we do that for training sets of different sizes using this polynomial with this order-dependent regularizer. So for small numbers of training samples, it will behave like a simple low-order polynomial, and it will generalize just as well. For large numbers of training examples, it will behave like a less constrained high-order polynomial, and it will generalize just as well. And so for any number of training points, it has optimal generalization behavior. And this is over also a variety of different types of training sets. Let's consider another example. Let's move beyond polynomials. So I mentioned that convolutional layers also exemplify this idea of restriction biases. You can derive a convolutional layer by starting with a fully connected layer, removing a bunch of parameters, and then enforcing parameter sharing. So you're basically replacing a dense matrix with a Toeplitz matrix when you do that. But let's suppose we don't want that exact constraint. So this corresponds to an assumption of locality and translation equivariance and image recognition. But maybe we don't think that we ought to exactly respect those constraints. We just want to be biased towards them. And if they can provide a good description of the data, we want to collapse down onto those constraints. One way of trying to do that naively could be to start again with the fully connected layer and then introduce a regularizer that penalizes the norms of any parameters that don't exist in the convolutional layer, as well as the distances between any parameters that otherwise would have been shared in the convolutional layer. And the strength of those coefficients, the lambda and the gamma, would tell us, how much we want to try to favor that structure. So that would be an example of turning a hard architectural constraint into a soft inductive bias and increasing the expressiveness of our hypothesis space. There are more elegant ways to do this. So we've proposed a mechanism called residual pathway priors that enables one to relax hard architectural constraints and turn them into soft biases. This approach places a prior distribution over the model parameters with a covariance matrix that lives in an equivariant subspace, Q, plus an orthogonal complement. And what we found that at the time was very surprising, but with hindsight maybe isn't so surprising, is that quite often we only needed a very gentle encouragement in the direction of the structured subspace here. And so even with the slightest of biases for a particular invariance, the model would work as well as a perfectly constrained model in a particular application setting. So if we're considering molecules, for instance, we know they're rotation invariant. If we use a residual pathway prior with a very soft bias for rotation invariance, it will tend to work as well as like a steerable CNN that is constrained to be rotation equivariant. The reason for this is because if the model can fit the data perfectly with that constraint and it pays any penalty for deviating from that constraint, it will just collapse down onto it. Of course, if you don't have the constraint, or if you're anywhere in between, this approach will work a lot better than having the hard constraint, so it will be much more automatic. A higher level way of representing this idea for model construction is to imagine that you route your inputs first to a restrictive layer, and you try to explain as much as possible through that restrictive layer, and then you pick up whatever is left over through a more flexible layer. This is another way of understanding conceptually how soft biases might influence the training trajectory. So in the far left panel, we have a flexible hypothesis space, but we have a uniform preference for certain solutions over others separately from how they fit the data. In this instance, we'll often see overfitting and poor generalization. In the middle panel, we retain the expressive hypothesis space, but we have stronger preference for certain solutions in darker green. This will help us achieve more optimal generalization behavior. In the far right panel, we have a restriction bias, which prevents us from overfitting, but it also prevents us from finding a very good solution to our problem because we're not representing our honest belief that the real world is going to have some complexity and nuance. And so we want an expressive model in order to capture that structure. And a good way of doing that is saying, well, many things are possible, even if we believe certain things are more probable than others. Okay, so far we've been talking about intuition, but all of this intuition can be formally characterized using generalization frameworks that have actually existed for many decades. It might take a moment to parse this slide, but we'll go through it very carefully. And I hope by the end of this slide, if not by the end of the talk, we'll all really understand what this means. So what this equation is saying is that our expected generalization error, like our test error, is upper bounded by our empirical risk, our training loss, plus this complexity penalty, which has a few terms in it. One is this log 1 over delta. So delta is the confidence of our bound. If delta is smaller, we're making this claim with stronger probability, and so our bound will get looser. One is n, the number of training data points. So as we get more and more training data points, there's less of a difference between the expected risk and the empirical risk. That makes sense. And most importantly, there's this log 1 over pH term, where p is some sort of prior density over hypotheses. That's something that we specify to evaluate this bound. And I think where a lot of confusion comes in trying to understand how these bounds work. So the prior here does not have to be used by the model that we're trying to describe. The model that we're trying to describe doesn't even need to be Bayesian. It doesn't need to be using any kind of explicit prior. It's really just a weighting function that we specify before we see the data. And if it's a bad description of the model's behavior, then it will have low density for the types of solutions that the model is finding, and the bound will be very loose. Any questions about that so far? By the way, this bound can be derived very simply. So I've been partly describing a recent paper I have called Deep Learning is Not So Mysterious or Different. In the appendix of that paper, just in a single sort of column, you can derive this whole bound just using a combination of Hoeffding's inequality and a union bound.
A question about the equation, because currently it seems like the implicit penalty, of course, gets bigger if you use bigger model, right? So current intuition seems to be that simple models are preferred, but actually that's wrong.
So what makes you think the complexity might get bigger with a bigger model here?
Just the text about it, but
okay, this is a point we'll talk about a lot. So let me know if I haven't answered that later on. So we've found,
I just want to ask you, you're switching, right? Like, you're no longer talking about, like on the previous couple of slides, you were talking about this method for finding the model and then rate and output the generalization bound or shows the bound. But the generalization bound is going a method for choosing a model which is not having that.
so the generalization bound will describe models that we're constructing, but the connection between this and what we've been talking about so far is that the bound importantly doesn't penalize an expressive model class. Instead, it focuses on what types of solutions might be softly preferred by the model versus things like parameter counting. So in other generalization frameworks like VC dimension, random macro complexity, we're essentially parameter counting. We're measuring the model's ability to fit noise. This kind of generalization framework can actually provide very tight bounds on the generalization behavior of models that are perfectly capable of fitting noise. Instead, it doesn't penalize the expressiveness of the hypothesis space at all. It just looks at what sorts of hypotheses are going to be likely under the model. Oh, of course, yeah. Mm-hmm.
Thank you very much.
Yeah. Okay. So the question then is, what prior should we use to evaluate these bounds? We can really use any kind of prior density we want, but many choices won't lead to very informative bounds on really large neural nets. We've found something called the Solomonov prior to actually be very useful for evaluating this bound. So the Solomonov prior is basically 2 to the negative power of Kolmogorov complexity divided by a normalization constant, which we know is going to be less than or equal to 1 by something called Kraft's inequality. So the Kolmogorov complexity is the length of the shortest program that can generate our hypothesis, and we can upper bound that by the stored file size, the compressed file size of the model after training. And so this allows us to interpret our bound as essentially saying, well, we want a model that is expressive enough to fit the data really well in a variety of settings to achieve low training loss, But we also want it to have a preference for simple compressible solutions that can fit the data. And I would argue that those are really the two key ingredients that will lead to good general purpose behavior in a wide range of different settings. And to some extent, transformers encapsulate this behavior. And interestingly, we'll see that as we make the transformer larger, it will actually increase its simplicity biases, its compression bias. And so quite often, I think people believe that expressiveness of a model and its inductive biases are in tension with each other. And I think that this intuition comes from being used to thinking about inductive biases as restriction biases. If we instead think about them as soft inductive biases, there's no reason that these two things can't go together. And in fact, they do in deep learning. And we'll see many examples of this. And I don't want to get ahead of myself too much, but double descent will be a really good example. I also want to emphasize that evaluating these bounds is really easy. So you just train whatever model you like, using whatever optimizer or procedure you like, using whatever regularizer you like, Bayesian or not, whatever. Evaluate the training loss. Measure the stored file size of the model after training, and then evaluate the bound. Okay, so here we have a visualization that sees how these two terms come together to form our bounds. So ideally, we want low empirical risk and a high degree of compression, and then we'll have a tight generalization bound. We see here in the right panel that models with more parameters tend to actually have tighter bounds. So we can make stronger generalization guarantees for those larger models. We also see that these bounds are giving us something non-vacuous for models with a really large number of parameters. Here we have 100 million parameters. In work after this, we actually considered models with billions of parameters. Pack-Bayes is related to this generalization framework I've been describing. So you basically can go from the bound that I've shown to Pack-Bayes by replacing this log1 over pH term with a KL divergence between some distribution over desirable solutions Q and some prior P. Q doesn't need to be the Bayesian posterior. It could even be a point mass posterior, and that would allow you to use Pack-Bayes to describe deterministically trained models. I think this is a common misconception about Pack-Bayes, that it only applies to Bayesian models or models that have distributions over their parameters. That's actually not true. If, however, you don't care as much about the precision of your solution, then you can get some bits back and you can get a tighter bound, and that's really the intuition behind Pack-Bayes. It's not exactly the same as this other framework if you sort of replace that term with the KL, but it's very close. The Bayesian marginal likelihood also has a direct correspondence to a Pack-Bayes bound. So the marginal likelihood is the probability that we would generate our training data under our model prior. Okay, so we've been talking about model construction quite broadly. It's enlightening to instantiate this with a Bayesian perspective. So from the Bayesian perspective, we want to place a distribution over solutions in a prior. Here we have our linear function, the first choice in that airline passenger example. We put a simple distribution of the parameters that induces a distribution over straight lines with different slopes and intercepts. We observe some data, we infer a posterior. In this figure here, we're conceptualizing all possible data sets on the horizontal axis and the marginal likelihood on the vertical axis. So as I said, the marginal likelihood is the probability that we'll generate our data under our model prior. So if we have that simple linear function model on the last slide, we'll not be able to generate many data sets, but because this is a proper normalizable probability density, we'll give those data sets a lot of mass. We could also imagine a model that spreads its mass very thinly over all sorts of different data sets. In pink here, that type of model won't tend to generalize very well. We can alternatively have a model that's very expressive. It can generate lots of different data sets, but it has certain potentially even strong preferences for some types of data sets over others. So convolutional neural nets could be a good example of that. Here I've shown that in green. Okay, so here now we see what happens as each of these three models is exposed to a data set. So the green model is expressive. It's able to represent something close to the ground truth corresponding to some setting of its parameters, but it'll also efficiently contract around that solution because it has reasonable inductive biases. The blue model is quickly constrained by the data, but it's erroneously constrained by the data. It's not able to represent something reasonable at all. The pink model casts a wide net. It's able to represent a good solution, but it's not able to find that good solution because its inductive biases are spread too thinly over all possible data sets. I would argue that the defining feature of a Bayesian approach is really marginalization. People often think of priors as what distinguishes Bayesian procedures, but priors actually show up everywhere. If you maximize a posterior, you're basically doing regularized optimization. Marginalization says that instead of using a single solution, we should use all solutions that are consistent with our data, weighted by their posterior probabilities. So in this figure here, you can see there are many curves that seem to be consistent with these regression data points. It would be hard for us to say, oh, we definitely want to use that one or this other one. And the sum and product rules of probability say we shouldn't. We should use all of them and we should weight them by their posterior probabilities. We can write this more formally in equation 6. Instead of using a single setting of parameters W, use all settings of parameters weighted by their posterior. Here, Y are our targets, X are our inputs. And this approach is going to give us a particularly different answer when our model is not well specified by the data. And I would argue that that's particularly the case in deep learning, because we have neural nets that have many different settings of their parameters that will provide complementary and compelling solutions to a given problem. And so this is when we most want to compute this Bayesian model average. We can actually see classical training as just a special case of this procedure where we have a point mass posterior approximation around the most likely setting of parameters in our posterior. And so that might be reasonable if our posterior is very concentrated around a particular setting of parameters. Okay, so now that we started to build up some principles for thinking about model construction, let's use these principles to unpack various different generalization phenomena that have been perceived as mysterious and specific to neural nets. We'll start with benign overfitting. So I've said that benign overfitting describes the ability to fit noise perfectly, but still generalize well on structured data. This isn't explained by Rademacher complexity, VC dimension, or many kind of conventional frameworks in learning theory. And it was famously demonstrated in the paper, Understanding Deep Learning Requires Rethinking Generalization. Let's consider benign overfitting, starting with that simple polynomial example. So we'll have a high order polynomial, in this case, a 150th order polynomial with that order dependent regularization. In the panel on the left, we show it very simple structured data. It fits that data using a very simple function that looks almost like a linear function because it doesn't need to use the higher order terms to describe that data. In the middle panel, we increase the structural complexity of our problem, and our model automatically adapts its complexity as needed to also provide a very reasonable fit. In the far right panel, I've just sampled pure uncorrelated noise. Our model is also capable of perfectly fitting that data if we say that it should. And so if understanding deep learning requires rethinking generalization, then so does understanding this basic polynomial. Benign overfitting is not something that's specific to neural nets. We can also exactly reproduce the experiments in that paper using Gaussian processes. So in the top row here, we have sample prior functions in panel A from a GP with an RBF covariance function. In panel B, we see the posterior predictive with some simple structured data, looks reasonable. In panel C, we see the fit with a bunch of corrupted labels. The GP predictive mean is able to perfectly run through those corrupted labels, but it doesn't really want to. And we can precisely quantify how much a model wants to fit data through this thing we've already been discussing called the marginal likelihood. How probable is that fit under our model prior? And so even though our GP can represent that red curve and use it to fit the data, it would be a very unlikely sample from our prior over functions. If we went back to panel A, we would have to sit there sampling prior functions for a very long time before we saw anything that looked like that red curve. But it does exist within the support of our model. Gaussian processes do beautifully encapsulate this principle of embracing expressiveness combined with soft preferences for certain types of solutions over others. By the way, soft doesn't mean not having strong preferences. It just means not excluding certain solutions. We can also apply Gaussian processes to that exact image recognition problem in that paper where we're varying the number of altered labels on CFAR10. So Gaussian processes can perfectly fit all those training sets with different numbers of corrupted labels. As we do that, as we increase the number of altered labels, we see that the marginal likelihood in blue here of the Gaussian process decreases. So it's less and less happy with that data, but it's still able to fit it and it's still able to generalize reasonably. We can still We can do the same thing with a Bayesian neural net. And as I mentioned, the marginal likelihood corresponds to pack-based generalization bounds. So we have generalization bounds that are tracking this behavior. So they get worse as model performance gets worse, but they're also able to explain generalization in the presence of these noisy labels. Okay, over-parameterization. At this point, it's hopefully becoming intuitive that we shouldn't necessarily be worried by having a model with a large number of parameters. Parameter counting is not necessarily a good proxy for model complexity. We've seen examples like these high-order polynomials where you still have this simplicity bias. Gaussian processes are, as we've seen in a number of instances, also a beautiful way to build a model that is like an infinite-order polynomial that does have strong simplicity biases. There's this observation that larger neural nets have stronger simplicity biases, and we'll touch on that more in a moment, but it's interesting to understand why that might be and how overparameterization does generally affect the biases of models in deep learning. So historically, it's often been believed that despite the non-convexity of the optimization objective and many parameter settings of a neural net that will overfit the data, achieve low loss, and provide bad generalization, we might be saved by the implicit biases of the stochastic optimization procedure, perhaps SGD or ATOM, or traversing through some subspace of solutions that are low loss and provide good generalization. I actually think that this is not primarily responsible for generalization in deep learning. It might play a minor role, but it's not as if deep learning would break if we weren't training these models with stochastic optimizers. Instead, I think it's how the design of the architecture modifies the structure of the loss landscape. So as you increase the number of parameters in the model, you end up increasing the relative volume of low loss solutions that do generalize well. And heuristically, you could understand this by imagining that you have two regions in the loss landscape over which the loss is low, one with radius RA, another with radius RB, and you could imagine that RA is larger than RB. And so sometimes these are called flat solutions. You can perturb the parameters, but you retain a low value of the loss. And flat solutions tend to lead to better generalization because by definition, they're more compressible. You don't need to represent them with as much precision. And if you can compress something, you can usually do that through regularities, et cetera, which will enable generalization. So as we increase the number of parameters D in our model, the volume of that first region grows roughly as RA to the D, and the second region grows as RB to the D. So RA to the D starts to really dominate in the loss landscape. And there's lots of empirical support for this idea. So there have been papers showing that if you do full batch gradient descent in deep learning, you can get almost as good generalization as if you use ATOM SGD. Of course, it's not something one would prescribe, it's not computationally efficient, et cetera, but we're talking about generalization. This group actually went a step further and showed that you could even do guess and check. So you could just randomly sample parameter vectors and then stop as soon as your loss was below a certain threshold. And this would work almost as well as SGD or ATOM. So that starts to quite, I would say, assertively show that the implicit biases of the stochastic optimizer might play less of a role than we had believed in the generalization performance of deep neural nets. And it also is suggestive of this picture. So if you're just throwing darts at the loss landscape, especially as you increase the number of parameters in your model, you end up being much more likely to fall into a low loss region that provides good generalization versus bad generalization.
Yeah, so the specific guess and check was that. So the specific guess and check method, was that for full batch or small batch?
I think it was full batch, but maybe they looked at both. I don't remember.
Right, and it's to go one step further, is that question like relevant to their findings, or was the finding independent of my previous question?
I mean, I think it would be relevant, but I think this is something that was controlled for. This wasn't work done by my group, but it was done in a way that was sort of controlled so that there would be a reasonable comparison with SGD.
Okay,
Full
thanks.
batch, I believe, yeah. Okay, so the last of these phenomena, double descent. So double descent describes a setting where as you increase the expressiveness of your model on the horizontal axis, generalization error in solid red here first decreases as you capture more structure in the data. It starts to increase as you start to overfit the data, and then it decreases again. And in that second descent, that second decrease, all of the models have essentially zero training loss in dashed red. And so this is really a clear example that's been hiding in plain sight of how increasing the size of your model is increasing its simplicity biases. Because in that second descent, since all the models are perfectly fitting the data, it can't be the case that larger models are generalizing better because they're more expressive. It has to be that they have some sort of bias that helps them find a different type of low loss solution that generalizes better. And we can actually measure what that bias might be using quantities like effective dimensionality. So the effective dimensionality of a matrix is essentially the number of relatively large eigenvalues it has. So it's the sum of lambda I over lambda I plus alpha. So the number of lambdas that are significantly above alpha, some threshold. And so that quantity tends to decrease in purple in that second descent. And so larger models actually are finding solutions with a smaller number of effective parameters, meaning that they're more compressible. And we can also track this behavior using generalization bounds. We can reproduce this behavior also using linear models and track it using similar quantities. Should a Bayesian model experience double descent? So I've been saying that our honest beliefs are we should always embrace expressiveness. And this might suggest that as long as we're representing our beliefs in a reasonable way, that we should see monotonic improvements in performance with increases in model flexibility. And in fact, this is actually what we do see if we do more exhaustive Bayesian marginalization for neural nets. So in orange, we have SGD. In pink, we have a Gaussian unimodal posterior approximation. We see a little bit of double descent, but it's less pronounced. In green, we see a mixture of Gaussians posterior approximations, so kind of a more thorough approximation of the posterior. We don't really see any trace of double descent whatsoever. Interestingly, the accuracy is also much better for the Bayesian marginalization approaches. I think there's sometimes this misconception that Bayesian methods are just all about error bars and uncertainty. They are about that, but it's also a different way to make predictions. And so if you're combining together many complementary and compelling solutions to a given problem, you ought to see an increase in accuracy as well. And we do actually see a very significant difference in accuracy between the green curve and the orange curve. Of course, there's a difference in computational expense as well, but not such a big difference between the pink and orange curve in terms of computation, about the same training cost, a bit more in test time cost. Okay, so we've been talking about what doesn't make deep learning different. We can also consider what truly does make deep learning different. And when I first asked this question, there were some good answers. So someone said representation learning. That's certainly something that really distinguishes neural nets, especially for high dimensional natural signals. It's very hard to kind of know what a reasonable measure of similarity might be in high dimensional spaces. Neural nets are very good at learning a reasonable similarity measure. And this can be combined with kernel methods and procedures like deep kernel learning. The structure of the optimization objectives is also really quite fascinating and different in deep learning. So we had this discovery called mode connectivity. It was believed that if you retrain a neural net with different initializations, you'll converge to isolated local optima, meaning that if you move away from any of those optima in any direction, you'll incur a really high value of the loss. So that's represented in the top panel here. We showed that there are certain subspaces where you can walk in particular directions and actually go from one optima to another without increasing the value of the training loss at all along the way. And so we see that here with a polygonal chain with a single turn in the left and a quadratic Bezier curve on the right. And so these aren't conceptual figures, these are actual figures. This is like a ResNet with about 10 million parameters on CFAR 100, and we're just showing slices through this very high dimensional optimization objective. Interestingly, the different points along these curves actually give rise to models which make quite different predictions on the test data. Of course, they make the same predictions on the training data to get the same loss, but they're different representations and they can be combined. And so this is just making the parameterization of what I'm showing here explicit. So we have a polygonal chain, for instance, on the left. We go from W1 hat to W2 hat, two different solutions we found by retraining our model twice. And we do that by varying t from 0 to 1. We find these curves by learning theta, and we can do that by minimizing our loss uniformly in expectation over the curve. Okay, and finally, and the one that I really want to talk about the most, is the relative generality of modern neural net architectures and what ought to go into general purpose learning. So I've talked a fair bit about how we can specify our model and its inductive biases towards good generalization behavior in particular settings. Now we're going to talk a little bit about to what extent this idea can be made very general and what principles ought to go into very general purpose learning. So the no free lunch theorems, as I've mentioned, are often used to argue against the idea of automation. There are many no free lunch theorems. The earliest and perhaps most famous was from Wolpert, and it says that every learner is equally good in expectation over all data sets sampled uniformly from a distribution over data sets. There are others like one in the Shayla Schwartz and Ben David learning theory textbook, which says that no single learner can achieve high accuracy on every problem. And these are often used to suggest that we need to build highly specialized learners for particular tasks, because if our model is doing really well in one setting, it has to be doing poorly in other settings. So do the no free lunch theorems preclude AGI? So I don't usually use the expression AGI. This particular slide I made in a workshop about AGI and whether it's possible. Well, in practice, we've seen exactly the opposite trend. So we've gone from handcrafted feature engineering to modality-specific architectures like convolutional neural nets for image recognition, recurrent neural nets for sequences, MLPs for tabular data, regression, et cetera, to essentially transformers for everything. And so the way that we've been developing our models in practice has gone in exactly the opposite direction of what might be prescribed by the no free lunch theorems. How is this possible? Well, intuitively, naturally occurring problems could involve highly structured data. If we were just to sample data sets from a uniform distribution over all possible data sets, we would mostly get noise. The real world is a small corner of all possible data sets. This structure also could be shared between different problems that we're considering. And so I think the key question then is, to what extent is that structure shared and at what level of abstraction? And so our contention is that the distribution over real world data is biased towards low Kolmogorov complexity, and that the models that we're constructing share this bias. So we've already seen this generalization bound where we find that if you are able to achieve low training loss and your model finds a solution that's very compressible, then you'll provably have good generalization. And so this says that even under an arbitrarily large hypothesis space, generalization will be possible if we assign prior mass disproportionately to highly structured data that might typically occur in practice. So we explored this idea in a paper called The No Free Lunch Theorem, Kolmogorov Complexity, and the Role of Inductive Biases in Machine Learning. And here I've summarized a number of our conclusions. So the first was that many different neural net models, convolutional neural nets, transformers, et cetera, MLPs, can significantly compress the labels of their data. There was a very surprising finding that convolutional neural nets, which were obviously designed for image recognition, can provably generalize well on completely different modalities of data, even tabular data, due to this simplicity bias. So you can take tabular data and just shape it as an image and apply a convolutional neural net to it and essentially measure the marginal likelihood of that data and show that it'll provably have reasonable generalization. And this is, I think, quite a striking example, because convnets in some sense are an example of tailoring a model to a particular domain, like having locality and translation equivariance for image recognition in particular. And those sorts of inductive biases don't apply to tabular data. But what could apply to tabular data is this bias for low Kolmogorov complexity. We found that GPT-3 and other LLMs generate low complexity sequences with exponentially higher probability than complex ones, and this is more pronounced with larger models. And even randomly initialized LLMs will tend to generate more compressible simple sequences. Worries about overfitting to benchmark test sets might actually be overblown. So there's a lot to say about that, but there's been a concern, I think, in the air for quite a long time that because certain benchmark challenges like CFAR, ImageNet, et cetera, are so popular, we might really just be indirectly training on test by comparing so many different models and possibly selecting from models that are not going to generalize well in other settings. And so this hypothesis was explored in a series of papers called Do CFAR Models Generalize to CFAR? Do ImageNet Models Generalize to ImageNet? And the authors of those papers created new CFAR and ImageNet data sets, trying to be as faithful as possible to the generating distribution of the original data sets. And then they measured essentially the ranking of models that had done well on the original benchmarks on their fresh data. And I think they and perhaps many others were surprised when these papers came out because the ranking was essentially unchanged. And although the performance degraded in a slight way by a couple percent, this was thought to be mostly because there actually was some minor distribution shift between these different problems. This can actually be explained using these generalization bounds. So something kind of wacky that comes out of no free lunch philosophy is that maybe you should do the opposite of cross-validation and you would get just as good performance since every model is equally good in expectation over all problems. And so this kind of made us wonder, well, what would happen if you were to compare millions of models, even hundreds of millions of models on a particular benchmark? How would that degrade generalization performance? And so essentially, you just get a union bound. So you multiply that delta in the bound by like a factor of how many models that you're comparing. And you get this kind of logarithmic growth in how the bound loosens with the number of models that you're considering. And so you can show provably that you could compare like hundreds of millions of models on a problem like ImageNet, and you would see a very, very minor degradation in performance for like new samples from that distribution. And so this suggests that actually, maybe we shouldn't be as worried about overfitting on these very popular benchmarks. And finally, we can design models that work well in small and large data regimes by combining expressiveness with a simplicity bias. We saw an example of that with the large polynomials. We constructed other examples of this using neural nets. Okay, so I've been saying that we don't need to have restriction biases and that perhaps a compression bias might be sufficient. We've seen a lot of striking evidence that this might be the case. So in a different paper, we had a measure for equivariance error that we were exploring called the Lie derivative. And we found in that paper that after training, vision transformers were actually more translation equivariant than convolutional neural nets, which sounds impossible because conv nets by design are translation equivariant. But they're not exactly translation equivariant because you have aliasing artifacts and edge effects and things like this. And so kind of amazingly, this massive model with no explicit bias for translation equivariance is finding solutions that are more translation equivariant than a model that has a restriction bias specifically for translation equivariance. And this can be explained by these large models having a very strong compression bias. And discovering these types of invariances is a really great way of compressing your data. We've seen this sort of behavior in a number of other settings as well. So a few years ago, we were curious what would happen if we just encoded numbers naively as strings and put them into GPT and had GPT extrapolate the next sequence of string tokens for time series forecasting. And we were really shocked to find that without updating the model at all, doing this completely in a zero-shot capacity, using only a model that has been pre-trained on text completion, we got comparable or even better performance relative to purpose-built time series models that had been trained specifically on the time series data that we were considering. And so the question really was, how is this possible? After we had that result, we explored how we could better do uncertainty representation through tokenization, like tokenizing individual digits in numbers separately rather than numbers as a whole. So you get this like hierarchical softmax that can represent very expressive multimodal predictive distributions, et cetera. And so that helped. But even the really most basic things that we were considering worked way better than we imagined they could. We had a similar result for materials generation. So in this case, we took a LLM that was pre-trained on text completion off the shelf, Llama 2, And then we represented atomistic data as text, so like locations of atoms and energy levels and so on, and fine-tuned on that. And with this model, we were able to generate stable inorganic crystals more effectively, again, than purpose-built models that had been trained a lot on domain-specific data. And we found that the text pre-training was an indispensable component of this pipeline in order for achieving good performance. And we tried to examine why in this paper. So it seemed that that text-based pre-training was actually very useful for discovering things like salient symmetries, like rotation invariance, for example, would describe this particular problem. And this comes from this compression bias. So in some sense, by doing text completion, the model is learning Occam's razor for in-context learning. And so it's able to do a very good job of things like compression where it's relevant. This also helps explain the performance for time series. So in time series forecasting, you have a very small amount of the potentially available information. And so you want a really strong simplicity bias. Interestingly, when I presented this result at the Flatiron Institute a few months ago, someone came up to me after the talk and said, well, we read your paper and we actually found out how to get rid of the fine tuning part of this. So now it's just like completely zero shot and it's just from text-based pre-training. So in summary, I believe that AutoML is really just ML. It's making the ambitions of our field explicit, and I'm very enthusiastic about doing that. I think we do need to be cognizant of the driving ambitions of what we're doing, and that will help us reason more sensibly about how we're going to get there. I think we can also start to understand how this ambition actually really is a reasonable ambition, despite results like the no free lunch theorems. And we can begin to have a prescriptive approach for how we can build ever more general models. So we've been discussing some of that so far. For example, embrace expressiveness, encoda simplicity bias. There have been different hypotheses for why deep learning has been so generally successful. One of these is called the Platonic representation hypothesis. So that's that like different real world problems are projections of some common underlying reality, like images can be described with pixels or with text, et cetera. So if you train different models on those respective modalities, you discover similar representations. That's not really my belief. I think actually different problems quite often have quite different low-level structure, like molecules are rotation invariant, images might be translation invariant. You have a 2, you translate it, it still has the label of a 2, et cetera. But what those different problems have in common is compressibility. And so if you have a strong compression bias, then you'll be able to discover those salient symmetries. This perspective can be used to resolve a lot of generalization behavior that has been viewed as mysterious in deep learning. We can also reproduce this behavior using other model classes. In terms of future directions, I'm particularly excited about automatically discovering scientific theories. I feel like this is one of the most profound and important things we can do with machine learning, and we've barely scratched the surface. So there's been a lot of amazing work on AI for science. Most of this work, including all the work that we've done in this space, describe using a machine learning model as some black box function estimator as part of some predictive pipeline for a particular downstream task. That's different than using our model to gain new scientific insights into our problem that we didn't have before that would generalize to other problems. For example, the theory of general relativity is actually needed for GPS to work. If we weren't correcting for gravitational time dilation, GPS would break within a few minutes. We probably could train a neural network to find these correction factors and make GPS work. But if we did that, we wouldn't really understand what was going on, and it wouldn't be nearly as valuable as the theory of relativity, which can propose all sorts of other different interesting applications and give us like a fundamental understanding of how things work. Like if I were to go 1,000 years into the future, the first things I would want to know are like, what do we understand about science that we didn't understand before? Like, do we have a new physics? Was string theory correct? Do we know how the brain works, et cetera? And machine learning can help us get there. But I don't think we've even really started to understand how we would approach that problem. It wouldn't be data-driven in a conventional way. It wouldn't look exactly like symbolic regression, et cetera. It would be kind of a new paradigm. And so I'm very excited to see that area of automatic scientific discovery really blossom. In the more short term, I think there are very promising directions around understanding how to do data generation really well. So I've talked mostly about how we design our models. We want to have expressiveness and simplicity biases, et cetera. But there's this other complementary question of what data should we train these models on? And there have been some very surprising findings in the last maybe 6 months or so in particular that show that for a given computational budget, you might actually want to exclusively train on synthetic data. And some principles are starting to emerge around this. Of course, intuitive ideas like we want diversity of data, et cetera, that we're training on, but also some other unintuitive findings like the structural complexity of that data might need to be very high for us to get a lot out of it. And that might seem intuitively at odds with the idea that we want our models to have some kind of Occam's razor bias, but I think they're actually compatible. We want our models to have a simplicity bias, but we want the data we're training our models on to be very information rich, at least in terms of structural information. And we might, in order to understand this better, need to design new ways of measuring information that will be useful for reasoning about the science of data generation. And that's something that I'm working on presently and I'm very excited about. So I'll finish the talk by asking a familiar question. So we have airline passenger numbers indexed by time. We're considering 3 different choices. Who's going to go with the linear function? How about the cubic polynomial? 10,000th order polynomial? Okay, very good. Thank you.